let us welcome Professor Bhaskar Das Gupta for his lecture.
So, thank you Anjali for the introduction. I have got a little notoriety because after I have written the book on mathematics, applied mathematics, then before telling that I teach engineering courses, people say that I teach mathematics. And this is getting fast. Okay. And after I started English proficiency program, that has become prominent. People remember me for that more than mechanical engineering, which is good actually. Anyway, you people want me to give a good lecture? Yes? Then I would request the last row people to come forward. Because if I see a lot of people close by, then I typically give a better lecture, comparatively better. Okay? So last row people, please come ahead a little. Okay. Don't worry about this time and schedule, etc. What I do normally is that whenever I teach a course, I make a website for that course, and everything related to that course I link there. And the semester schedule also stays there. Sometimes the names of the teaching assistants are also there. Okay? And after that I leave it there till I teach that course next time. So if I don't teach this course for next 3 years, till 2023, it will be written like this only. Okay? So whenever I update, whenever I make any change, whenever there is a new set of primary clientele, then I change it. And secondary clientele, like you, keep on visiting it all the time, because even if no course is going on, you are most welcome to enter there and learn whatever you want. So that means that after you finish this course here for 1 week or whatever number of days you are here, and go back, and then if you feel that there is something which was told in this course and you thought that you understood at that time, and later you thought that you are getting a little confused about it and you want to look at it once more, you can look at it. So in order to be able to look at it, you can note down this. Okay? But only till this point you are seeing. So how do I tell you the rest? If I go there, then will it show up? Yeah, it does. So where is that? No, it did not show up. Okay. So if you want, you see home.iitk.ac.in/tilde-dasgupta. That is my home page. Okay. Not that everything is updated there, but that is supposed to be the home page where my information should be there. But then under that, if you go teaching and robot 1, then you come there. If you go only teaching, then you get a long list of courses which I have taught, I am teaching, or I am likely to teach, and then you can come here and introduction to robotics, you reach the same place from where we started. Okay? So this is how I can help you after you go back from here. Oh yes, list of students is there, but that's irrelevant to you. So we directly go to what is our interest for this particular lecture. So, this has been already discussed with you by my colleague Dr. Datta. I will just quickly revise what has been done and then I will go to my own business. Okay? So, fine. So, in order to do any sensible robotics, you need to represent rigid body motion. Okay? Rigid body motion has two components, rotation and translation. Translation is easy, rotation is a little complicated. So, we first attack rotations. So, rotations, we start with plane rotations, 2D rotations, okay, in xy plane, and there we say that there is a body in which there is a point P with coordinates xy, Cartesian coordinates xy, polar coordinates r alpha, related like this. Now, if that body rotates about the z axis, which in the plane simply means the origin, by an angle theta, then all points on that body can move, okay, except the point which is here. In particular, this point also moves, and suppose it goes to P prime. And then the task of this analysis of rotations is basically to find out the coordinates of the new point where it has moved in terms of this angle by which it has rotated. And in that xy or alternatively r alpha are already known. So, just school geometry will tell you that the new coordinates x prime y prime you can get like this, and these two expressions happen to be linear combinations of the old coordinates x and y. So, if they are linear combinations of x and y, then you can nicely put x and y in a vector, and the coefficients in that those linear combinations you can put in this coefficient matrix, and then say that when a rotation about theta, through theta takes place, then or about the origin, then the point coordinates change like this. This position vector gets multiplied by a matrix, let us call it R, written in this stylish fashion. You can write it whatever way, and this matrix we call rotation matrix. If you carefully check the content of this rotation matrix, you will find that its first column is a vector, right, with magnitude 1. Second column is also a vector with magnitude 1. And if you take this vector dot that vector, what do you get? 0. Fine. So, each column is a unit vector and the columns are mutually orthogonal. This much defines a matrix as an orthogonal matrix. So, you say that rotation matrix will be an orthogonal matrix. And then what is its determinant? 1. Not minus 1? No, not minus 1. So, determinant positive 1. Orthogonal matrix can have determinant either 1 or minus 1. So, in this case it is 1, okay? And for a rotation matrix it will always be 1. For what kind of matrix it will be minus 1, can you think? Where left hand looks like right hand. What is the event? What is the event in which, through which? Reflection, okay. So, like rotation, there is another thing called reflection, okay. And through rigid body motion, reflection never takes place, okay. So, that is why the determinant is always plus 1. So, a rotation matrix is characterized by orthogonality and positive determinant, okay. Now, we have seen that a rotation in 2D can be represented with a 2 by 2 orthogonal matrix with determinant plus 1. This 2 means this 2 by 2, okay, this 2D. because we are discussing in plane. Its converse is also true. Any 2 by 2 orthogonal matrix with determinant plus 1 will represent a valid rotation. Okay? That makes sense, because if it is a 2 by 2 orthogonal matrix, then each column will be a unit vector, and a unit vector alpha beta, you can always call alpha as cos of some angle, then beta will be the sign of that angle, because it is a unit vector, and therefore you can, if alpha beta gamma delta are given, then actually you can work out that angle theta, and alpha beta gamma delta will have some conditions which they will satisfy due to this orthogonality. Okay. That is, alpha square plus beta square is 1, gamma square plus delta square is equal to 1, then alpha gamma plus beta delta is 0, that is orthogonality, right. So, fine. Now, if you want to give one rotation like this by theta 1, then you multiply with this matrix. After that, you give another rotation by theta 2, you make another such matrix and multiply on that side. Another rotation theta 3, multiply on that side, and so on. So, this is how you compose successive rotations. Okay? Here there is something. Here in all cases, the rotations are represented in the fixed frame of reference, the frame of reference which itself is not rotating. Okay? That is how we are normally supposed to think, normally expected to think. Okay? However, sometimes it may happen that you are describing the successive rotations from the viewpoint of the body itself which is rotating. Okay. In that case, you can analyze and see that the rotation order, the multiplication order will be exactly the other way around. Okay. If you want to invert a rotation matrix, then simply you have to take the inverse of this, which in this case is simply transpose, because the matrix is orthogonal. Okay. In 2D, it simply means that if the original rotation was by theta, the inverse rotation will be by minus theta. Okay. But this preparation is actually for 3D, okay, where we will go, but before that, let us combine rotation and translation together. So, 2D rigid body motion, if you want to consider, then you have to consider translation and rotation. So, the body rotates about the origin and then translates by a vector, moves linear motion by a vector t. Then this is the situation, rotation plus translation. Okay. So, here there is a formulation bottleneck, because if there is one rigid body motion r1 t1, then there is another r2 t2, and another r3 t3, then successive rigid body motions, this, if you need to compose and find out what is the resultant rigid body motion, resultant rotation and resultant translation, then you have to do something very funny. Like, you take the point and operate it through rp plus t for r1 t1, then you get this point. Next rigid body motion comes r2 t2. So, you multiply this is r2, then add t2. Then next is r3 t3. You multiply with r3 and t3, and you can see how the expression is going big and clumsy. Okay. So, this is the formulation bottleneck which people settle by, see, from this, if you want to find out what is the resulting rotation, then you have to work out this thing, open it and get separately the coefficient of p and whatever is left. Okay. So, that is troublesome. So, remedy people worked out by working out homogeneous transformations. So, before homogeneous transformations, what we do is that under the position vector x y, we put a dummy 1, okay? And then we say that rather than p, we will represent the original point as p1, and rather than p prime, we will represent the final transformed point as p prime 1. Okay. And then we actually write the same expressions. X prime is x cos theta minus y sin theta plus Tx. Okay. And y prime x sin theta plus y sin cos theta plus Ty. The first two parts were in the earlier plan coming from here, and the third part was coming from here. Now we have put everything together, okay, and the last one is trivially given by 0 plus 0 plus 1. So that is a dummy row which we have inserted, and a dummy equation we are getting 1 equal to 1. Fine. That is, you simply do not bother about it. That is there, that is going to be satisfied. The last row will typically be 0 0 1. Okay. Now you see, if you take this 3 by 3 matrix, you find that this part is R, this part is T, this is a 0 row, and this is 1, and that is what you keep. This is R, this is T, this is 0, 0 row, 0 0, and this is 1. And you find that the product is RP plus T, which expanded notation you get from here, and the lower row gives you 0 plus 1, which is this. Fine. So now this entire a little bigger matrix, okay, you have put everything in a box, you call that as T. This is the homogeneous transformation matrix. Okay. And now you say that rotation and translation, that is rigid body motion, complete rigid body motion can be represented by the pre-multiplication with this transformation matrix, where the respective parts are assembled like this with lots of dummy things at the bottom. Okay. And now that formulation bottleneck is gone, because what you will do, for the first rigid body motion you will compose and put in box R1 T1 0 1. For the second you will put R2 T2 0 1, and so on. And then when you want to find out the transformation, then you will first multiply with R1 and T1, that full box matrix 3 by 3, then on this side T2, on this side T3, and so on. Now think of 3D. If you consider rotation only, just like the way we did in 2D rotation, then if the rotation is about z axis only, the same rotation which we considered earlier, now we are showing it as z axis, okay, then what will happen? X coordinate will move like this, that only as earlier, y coordinate as earlier, z coordinate will not change, right? Because if the rotation is about z axis, then z coordinate will not change. Okay. So now these three things you put together and you get like this. Since in the first two equations there was no component of z, you get 0 0 here, and in the third component there is no component of x y, so you get 0 0 here, and since here the coefficient is 1, remains same, so this is 1, and you get x prime, y prime, z prime. So this is rotation about z axis, right? Like this. Okay. Similarly, you can work out rotation about x axis. Oh, in both places it is the same thing. Rotation about x axis, rotation about y axis. And then you can work out arbitrary rotations through compositions of such individual component rotations. And composition rule, something that I pointed out earlier once, for successive rotations, if the rotations, individual rotations are described with respect to the fixed frame, which is not rotating, then it is this way, because we are representing vectors as column vectors and matrix vector multiplications we are representing as matrix into vector. Vector is appearing on the right side. That is why successive transformations will come by left multiplication. That is the only thing possible. Okay. And if the local frame itself describes the successive rotations, then the composition is like this. Okay. So, that means that rotations R1, R2, R3, R4 described in fixed frame, whatever final rotation that will give, okay, if the same rotation matrix, if the same individual rotations are given with respect to the moving frame, the frame which is itself rotating, that is, for all this analysis, for every rigid body you attach a frame. Okay. So, if the rotations are described in the frame of the body which itself is rotating, then it is like this, and this thing is operated over the point of the body. So, that means that rotations with respect to fixed frame R1, R2, R3, R4 are equivalent to rotations about the moving frame in the opposite order, okay, because it is actually this way. Okay. Here also you compose rigid body motion in the same manner. So, this vector is now 3 plus 1 4 dimensional, and this vector also is 4 dimensional. So, this is 4 by 4 matrix. Okay. So, this block, this 3 by 3 block is the rotation matrix giving these 3 unit vectors. So, this part is orthogonal, right. This is the translation vector which can be anything, and below you have 0, 0, 0, 1. So, this is the homogeneous transformation. So, again according to the same plan, we have compositions of rigid body motions. If each rigid body motion refers to the fixed frame, then it is this way. If each refers to the local frame of the body, the motion of which we are discussing, then it is this way. When you want to invert, inversion means what? Physically, it means that one rigid body motion was given to the body, okay, and then you are asking, oh sorry, what rigid body motion now we have to give to take it back? That transformation will be the inverse of the original one. Okay. So, that is T inverse. So, inverse of this turns out to be this, or you can represent it like this, because inverse and transpose are the same thing. This is actually very easy. You can think of it in two ways. You can verify it in two ways. One, mathematically, okay, and two, physically, seeing its sense. So, if you want to mathematically verify it, then you see you are trying to get the inverse of this matrix, and I am telling you that this is the inverse. So, if it really is the inverse, then what you can do? The original matrix and the new matrix you multiply, and you should get identity, right. In this partitioned form, in the identity, this part, the leading 3 by 3 block will be identity matrix of the 3 by 3 size. This will be all 0, this will be all 0, and this will be 1. That will be the identity, right. So, just try multiply. You see, this matrix we are mentally multiplying with this matrix. So, R transpose, that is identity, because R transpose is R inverse. So, R transpose, or look at it from this side itself, R inverse identity plus T into 0, that is 0. So, the leading block is identity I3. Then what will come in the second block here? R times this, and what is that? R inverse is identity into T, that is T, and this minus sign. So, you get T minus T, right, minus, okay, R this minus T, yes. So, minus sign remains, R transpose RR inverse is identity, so it is minus t. Minus t plus t into 1, that is t. So, minus t plus t, so that is 0. So, in this place, in the product you will get 0. Below you will get this row vector 0 into R inverse, 0 into anything is 0 only, plus 1 into 0, 0. So, all these three places in the product you will get 0. And this final, this position 0 times whatever plus 1 times 1, 1. So, you have got that. So, in the product, in this leading part you have got 3 by 3 identity matrix, here you have got all 0, here you have got all 0, here you have got 1. So, that shows that this is indeed the inverse of this. This and this are the same thing, because R is orthogonal. Okay. This is how you see it mathematically. If you think in terms of geometrically or physically, then what you will say? You will say that suppose both the bodies are originally in the same configuration. Okay? Both bodies have x axis here, y axis here, z axis here, origin here. This fellow's frame and that fellow's frame, both are here only. Now, the fixed frame remains there, the body rotates and translates. Okay? Its x, y, z axis go somewhere else, origin also goes somewhere else. Now, when you say inverse, you say now this fellow looks of a different orientation at a different position from here. Okay. How does this looks from there? Right? So, that is the inverse. So, this fellow looks this x, this y, this z directions and this position. How does this guy, fixed guy, look from there? So, orientation, it will be the inverse, and that is why here you have got inverse. Okay. Position, it will be, if from here that point, that origin, from this origin, if that origin looks like 2, 3, 4, then from that origin this vector will be minus 2, minus 3, minus 4. But then you have to keep in mind that it is that guy seeing that, not this guy. So, his basis, his way of describing vectors is R transpose, R inverse. So, from 2, 3, 4 you get minus 2, minus 3, minus 4 by this minus sign, and it is from there it is being seen from that fellow's x, y, z directions. That is why the vector is transformed by R inverse. Okay. And below anyway, in the last row anyway 0, 0, 0, 1 will come. So, this is how geometrically you make sense of this inverse. So, that means that even inverse is very easy for transformation matrices. Okay. So, rotation matrix as well as transformation matrix with the 4 by 4 rotation plus translation, the transformation matrix has actually two roles. One is that it can actually represent a physical rotation in which things move, okay, and the old points get transformed to new points through that rotation matrix. In another way, in another role, the same matrix represents the orientation of a body. In this frame, you can describe the orientation of this body by saying that if I take the unit vectors of that frame, the coordinate unit vectors, x axis, y axis, z axis, unit vector along x axis, unit vector along y axis, unit vector along z axis, and describe it in this fellow's x, y, z axis, because that x axis may not be in the direction of this x axis. Okay. That will be perhaps in a direction 2 by 7, 3 by 7, 4 by 2 by 7, 3 by 7, 6 by 7. Okay. So, in this x, y and z. So, that will be the first column. Similarly, whatever is that fellow's y axis unit vector, when you describe this in this x, y, z coordinates, this x, y, z components, that will be the second column. Similarly, the z column, z direction will be the third column. Okay. So, the rotation matrix actually can describe the orientation of that body. Now, what is the relationship between the matrix which represents a real rotation, actual physical rotation, and a matrix which represents the orientation? What really happens is that if the orientation of a body, its frame of reference, in another frame of reference, is described by a particular rotation matrix, that means that if both of them are put first in the coincident position, coincident orientation, then that rotation matrix, pre-multiplication of that rotation matrix will actually put this other body in the given configuration. Okay. So, if you start with both of them as coincident, the x axis coinciding, y axis coinciding, z axis coinciding, and then if you give a rotation matrix, if you give a rotation by R, matrix R, then wherever it goes, after going there, its orientation will be represented by that same matrix. Okay. So, that is how it works. And the same thing operates for transformation matrix also, including rotation as well as translation. So, representation of an actual rigid body motion with respect to a frame, and after that has taken place starting from a coincident configuration, then the representation of its position and orientation in the original frame. And you see, this is a dynamic event and this is a static configuration. Okay. Both are represented by the same matrix. Okay. So, from the coincident position and orientation, this dynamic event takes the moving body to a new configuration which is described by the same matrix. Okay. With this background, we come to direct position kinematics of robot manipulators. Okay, till now any question? Of course, there will not be many questions because this is something which I have actually repeated over whatever already has been done. Okay. So, in robot manipulators, in robotics, when you try to describe relative motions among different rigid bodies, I am talking about rigid bodies only. I am assuming that all the links in my robot are rigid. Okay. But then there can be robots with flexible links also. Okay. That will have some more complications where we are right now not going. Okay. So, whenever we try to analyze anything, what we do is for every rigid body we attach a frame of reference, by using which we will be describing its position and orientation, and from that frame of reference we will be describing the positions and orientations of the other bodies, positions, orientations, motions. Okay. So, now the links will be connected to each other, to one another through joints. Now, most of the industrial robots have joints and links connected in series. There are other kinds of robots possible, okay, in which you have some connections in series and then some connections in series connecting together, they are making a network kind of connection, that is possible. Closed loop manipulators, they are called closed loop manipulators, closed loop robots, parallel robots, but they are more complicated things. There also the fundamental discussion that we are going to make now is going to remain valid. So, you describe in such manipulators also, complicated ones also, links and joints in series, and then if two series coming from two different paths meet by a closed loop, there you put some constraints. Okay. So, in the case of open loop chain, open loop manipulator, that closing will not come except when the final link, the robot hand goes and holds something, then there will be the closure. Okay? Fine. So, in such situations, if you have only open loop, open chain, okay, one link, that is the frame, then one joint, say joint 1. So, the frame is say link 0, okay, then joint 1, then link 1, then joint 2, link 2, joint 3, link 3, like that. Finally, you will go up to joint n, link n. Link n has the hand, which is supposed to hold things and move. Okay. Now, it is important to describe the motion of the links relative to one another, okay, and those relative motions will be taking place through the joints, right. Now, what kind of joints you think you can actuate? See, there are many joints in mechanical connections: revolute, prismatic, cylindrical, planar, spherical. Spherical is ball and socket, okay, and so on. But only two kinds of joints are really, easy to actuate. One is revolute and the other is prismatic. Okay. So, revolute joint is characterized by a line axis about which relative rotation can take place. Prismatic joint also is characterized by a line in space along which translation can take place, relative translation. Here, in the case of revolute joint, it is the axis about which rotation takes place. In the case of prismatic joint, there is an axis along which, not about, along which relative translation takes place. Fine. So, in either case, it is a line. Now, one such joint, okay, the joint axis of say joint I minus 1, okay, connecting links I minus 2 and I minus 1, and the next joint, which is joint I, connecting links I minus 1 and link I. So, these are two successive axes. Okay. In this axis, there is the origin of one frame of reference. In the next axis, in that line, there is an origin of the next frame of reference. So, the real thing that we need to do is to describe this frame of reference from the perspective of this frame of reference, the position of its origin from its origin, and the directions of its xyz axis from its perspective, its frame of reference, as components in its xyz frame, the xyz directions. So, that is what this shows you. So, this is link I minus 1, after which there will be link I, and before which there was link I minus 2. Okay. So, this is axis I minus 1, that is the axis of the joint I minus 1. It may be revolute or prismatic. Similarly, this is the joint axis I. It can be revolute or prismatic. Okay. Now, in the xyz frame here, you need to describe the xyz frame here. Before that, there is a convention how to put that xyz frame there. So, to work out a standard sensible arrangement to put the frames describing, fixed to each body, we need to have some policy, some system. The system that people agreed upon is dependent on the kind of relationship two lines in general in space can have. Okay. If you are given two lines in space, then in general what relative disposition you would expect between them? Typically, you would not expect anything special. In the general case, you will not expect anything special. You will not expect that they will be parallel, right? You will not expect that they will be intersecting. You will not expect that they will be in a plane, right? Two lines can be in different planes, making some angle, okay, not intersecting like this. So, these are two skew lines, skew is the word, okay, which describes the relative disposition between two lines, two axes, which are not in the plane, not in the same plane. Okay. So, if you try to describe the distance between these two, then how do you do that? You find out the length of the common normal, common perpendicular. Okay. So, the way I am holding this, if you work out a line like this, then you can find it to be at right angles to both of the axes, both of the lines. That is a common normal. So, now here between these two axes, I have designated the common normal like this from here to here. You know, in 2D plane, when you make 3D picture, you can never show right angles correctly. Okay. So, you have to force it by putting things like this block and this block, because if you, for example, when you are trying to sketch a matchbox, okay, children's picture, okay, children's sketch, then you will make parallelograms and call them rectangles, okay, and you will have to show that by this kind of forced right angles, okay, fine. So, this is a common normal. This is one axis, this is another axis, okay, this is a common normal. So, this common normal is this length, this distance is one important parameter that characterizes, there are other parameters that characterizes a relationship between these two frames. Okay. So, you call it link length, because why it is called link length? Because if the two axes were not inclined like this, if they were parallel to each other, then indeed this would be the length of the link, right. So, that is why you call it link length. And then what is spoiling that nice parallel situation? There is an angle by which this link has got twisted away. Okay. So, you call that the twist angle, and if the two z axes were parallel, then you would say that there is no twist, zero twist. In this case, there is a twist. So, what is a twist? Twist angle is the angle between the two z axes. But then two z axes are not in the same plane. When there are two lines like this which are not on the same plane, how do you measure the angle between them? You can move one of them parallel to itself, so that finally they cut, and then you measure the angle. That is the angle which is the angle between the two lines. So, fine. So, move this guy parallel to itself along this, if you move, then you get this, and this is the angle, okay, between this z axis and this z axis, or its parallel. Okay. So, this is the twist angle. So, these two, first of all, are two parameters. There are two more. How? We use the convention that for the frame of reference which we want to attach to this link, okay, the z axis is taken along the joint axis. Okay. So, this is the joint axis of the joint I minus 1. So, you put z I minus 1 along this. Origin will be on that axis somewhere. Where to put that origin? So, you take it as the common normal, foot of the common perpendicular between this and the next axis. Okay. Axis I minus 1 and axis I, between them the common normal that you have worked out, the foot of that perpendicular, common perpendicular here is the origin of this frame I minus 1. Okay. And this direction of the common normal is taken as the x I minus 1. Okay. After we have fixed z direction and x direction, we actually have effectively fixed y direction also, because from the z direction, if you move towards the x direction by 90 degree, okay, like this, then the direction along which the screw will move, that will give you the y direction. Z cross x will give you y. Okay. So, y got fixed in the process by fixing these two. Okay. So, you have got come here. From here you have come here. So, origin, choice of z axis, choice of x axis, everything done. So, first the choice of z axis, that was obvious. Then from the common normal you got the position of the origin along this line and the direction of x, and that in a way described the y direction also. Now, you have come here, but then here you have come, but you do not expect the next origin to be here, because the origin of the frame I in general will not be possible to be here, because by the same rule the origin of the frame I will be somewhere along this axis, and that will be decided by the common normal between this axis and the next one. So, you do not expect that this origin will be here. So, it will be somewhere in a little offset, and that is called the frame offset. So, if you bring it here, then you still do not find the origin. To get the origin you have to move by an offset, that is called the frame offset. Okay. Now, what you do is in order to describe this frame of reference, in this frame of reference, its position of this origin and orientation of its axis, what we can now do is that first of all we can turn this frame of reference through alpha to make the z of this parallel to this. Then you will move this up to this, so like this. So, that is turning by this twist angle. After that you can, now then what will happen, z of this will become parallel to this z of this. Then along this x axis, now this rotation of this frame was about the x axis, you see the z turns like this. So, y also will turn like this, this remains firm. Okay. So, this rotation is about x axis, okay, through this angle, that is the twist angle. Then z of this becomes parallel to z of this, along this it falls now, and then this frame of reference you move along the x axis like this. Then what happens? The z axis moves parallel to itself and comes and coincides with this axis, this z axis. Still the origins are at two different places. Okay. The third will be, you move the origin, move the frame along this z axis, and by now through these two steps this z also has come here only. Okay. So, that the origin moves to that origin, and this distance is the frame offset. After you do all these things, what has happened? This fellow z became parallel through this turning, this fellow z became coincident with this by this movement, and then through this motion along the new z axis through this frame offset d, you have come and brought the origin also. Now, z is coinciding, origin is also coinciding, but x and y are still showing in a different way. Okay. And that is where it will show when you find that this x after that first rotation has come like this, and this x, okay, it has come like this. So, the x remained the same thing, because about the x the rotation was given. So, x is this way and this fellow's x is this way. So, this is the angle. So, by this angle if you now turn, then x axis also will coincide. Okay. So, there are 4 steps. First, rotation about the x axis through the twist angle, then translation along the same x axis through the link length, then translation along the new z axis through the frame offset, and finally the rotation about the z axis by angle theta I, which is perhaps a joint variable, joint angle. Now, you see that these two are fixed by the design. okay, design of the manipulator, always. Out of these two, this will be fixed if the joint is revolute, then this will be variable. Okay. That is why here it is written variable / parameter. On the other hand, if the particular joint is prismatic, then this will be fixed, it will be parameter, and d will be the variable, right, because it is prismatic joint. In particular, you may make note that these two rotations and translations are about and along the same axis, and that is why these two you could have actually given in the opposite order also, it would not make any difference. So, this is a body. Okay. If I rotate it about a particular axis and translate it also about the same axis, then in whichever order I do it, it will not matter. See, I am translating and then rotating, okay, or I am rotating and then translating, it is the same thing. On the other hand, if the directions, if the axes are different, then it will make sense, make a difference. Suppose the axis is through this bottle's axis, okay, and the translation direction, suppose it is vertical, okay. So, you see, I am rotating and translating, okay, and now if I use this axis, it will be difficult to see. Let me see how. Yes. So, what is happening is that as I am now, I am saying vertical, but I need several hands. Anyway, so say I am taking this for the rotation axis, okay, vertical, and but when I say vertical, I mean the axis, the direction making, say something like 60 degree with this bottle, okay. So, first rotate like this and then translate like this, okay, or I now what I do, what happens is that if I rotate it like this, then its frame of reference, its axis, x, y, z axis will change. So, in the general case, the translation rotation will not be commutative, but if it is the same axis, then even the other way around you could have given the rotation and translation. Similarly, in this case also, because here also this axis is the same, okay. So, when you put this, I wonder how, so yes. So, this rotation this and translation this, if we write that, rotation about x axis, that is this, right. I am writing C alpha for cos alpha shortcut, and if there is no rotation, then there is this, and bottom row is anywhere dummy, okay. So, translation, pure translation having no rotation component. So, this leading 3 by 3 part will be identity. That is what you would get if you put alpha equal to 0, okay, cos alpha 1 1, okay, and sin alpha 0 will give you this, and translation, okay. So, along x axis the translation, this is supposed to be A, not alpha, okay. So, the translation is along along x axis. So, the first component is A, second component, third component 0 0, because they are the components along y and z directions. The fourth row is dummy. When you multiply these two in this order or in that order, you get that matrix which is here. Okay. You can see actually the two parts. This is that rotation part which is coming from here, and this is that translation part which is coming from here. Similarly, rotation about z axis is sitting here. Okay. Rotation about z axis. So, this is 1 above which it is 0 0, on this side 0 0, and this part is that cos minus sin sin cos. Okay. And translation along z by d is 0 0 d. Okay. When you multiply these two, you get a very complicated looking matrix, okay, with the top 3 rows having some complicated expressions, bottom row being 0 0 0 1. Okay. So, the top 3 rows, whatever you get in the leading 3 by 3 part, that is the rotation matrix that actually shows the orientation of this frame of reference in terms of this unit vector, this unit vector, this unit vector expressed in these 3 components. Okay. And the fourth column, okay, the first 3 entries will show the position vector of this vector, position vector of this point from here, this vector joining origin to origin, as expressed in this frame of reference. Okay. So, this is what is called the link to link transformation. Okay. And like that, from the base link, frame link 0, link 0, you can describe 1. From frame 1, you can describe link 2 or frame 2. From 2, you can describe frame 3, and so on. Finally, when you describe the hand frame, then the all the matrices, all such 4 by 4 transformation matrices, when you multiply like this together, then this product will give you the position and orientation of the last link, the hand, the end effector frame, in terms of the base frame. And this is what is known as the direct position kinematics. That is why it is called the direct position kinematics, because it describes the position and orientation of the end effector when the joint variable values theta 1, theta 2, theta 3, theta 4, etc. are given. Because other than one of the parameters among these 4, other than one of them for revolute joint this, for prismatic joint this, other than the variable one of them, the remaining 3 for every joint is constant anyway. Okay. So, this whole thing that you are getting, in that this matrix is actually a function of theta 1, because alpha 0, a 0, d 1, the other 3 parameters are constant. So, here only theta 1 is variable, if assuming that the first joint is a revolute joint. Similarly, if the second joint is also revolute, then here theta 2 will be the variable, alpha 1, a 1 and d 2 will be constant. Suppose the third joint is prismatic, then here alpha 2, a 2 and theta 3 will be constant and d 3 will be the variable. So, in terms of those joint variables, you can describe the position and orientation of the end effector. First 3 columns will give you the orientation, and the fourth column will give you the position. So, end effector position and orientation through this exercise you can describe in terms of joint variables, and that is direct position kinematics. Symbolically, in an abstract fashion, you can write like this, where this fat theta has all these fellows, theta 1, theta 2, theta 3, etc., the joint variables, and this x vector has the position vector x, y, z of the hand from the base frame origin and 3 angles which will together represent the orientation of the hand, right. So, this is direct position kinematics done. Okay. So, this is one possibility of describing the orientation phi theta psi in this manner. There are other possibilities. This particular one is called roll pitch yaw angles. Okay. Why roll pitch yaw angle? Because that has been taken from the maritime history. In navigation, if this is the boat, okay, then if the boat moves, rotates, if the boat rotates about the axis from its back to front, then it rolls. You say this is roll, okay. And if it rotates about this axis, then we say that it pitches, it is pitching, this motion is pitching, okay. These two are dangerous, right? Water will come in. And if the boat rotates about the vertical axis, that is not dangerous, that is something which you normally do, that is steering, okay. That is yaw. Yaw means steer, okay. So, from the maritime history, people have picked up this roll pitch yaw term, and that is very much important for aircrafts also, okay. Now, when you want to do inverse kinematics, yeah, is it tea time? Good point, okay. So, we will have a break and then we will discuss inverse position kinematics, and then maybe we will use this interesting thing and solve a problem, okay.